Okay, enough about generic functions. We will also use them throughout this course, also in the course project, so that should be getting clearer and clearer the more we work with it. The general idea hopefully is clear by now already. Generic functions aren't everything we can use though. We also got generic classes, and therefore let's see how we would create such a generic class and why we could do that, why that could be useful for us. We could be creating a storage class here. A class, let's say, which has a private property data, which in the end will hold an array of data. And then it has an add item method, which takes an item, and that should be added to data with push, let's say. And we have a remove item method, which takes an item, where we could say this data splice, and then we just need to get the index of item here and splice one element. This is how we can remove an element from an array. And of course, get items, where I return, let's say, a copy of this data, like that, with the spread operator you learned about. Now we can do that, and we're getting a bunch of errors here. We're getting a bunch of errors, now for one, because the name storage is a reserved name, so let's name it data storage. That's easy to get rid of. Now we also get an error here because we're not saying anything about the kind of data we're storing and which type item has here. And that's exactly where we can turn this into a generic class, because we might not care about the type of data. We want to make sure it's uniform data, so it's either just strings or just numbers or just objects, but other than that, I don't care about it. So here we could turn this into a generic class by adding angle brackets after the class name, and then again, T, U, whatever you want to use as an identifier, and add this here as a generic type. Now here we can say this here is an array of type T, so it stores data of that generic type in it. Therefore here we add such data and we try to remove such data here. And therefore here get items correctly is inferred to return an array of generic types. And now we can create different storages. We can have our string or our text storage here by calling new data storage, setting that generic type to type string here, and then here in text storage, I can call add item, and if I try to add a number, I get an error because I'm saying that this will be a data storage which only stores strings. So I can indeed store max here, and maybe also store manu, and then call text storage remove item max, and then console log text storage get items. And this should all work if we save that, because it's a generic type, and indeed at the end we just have manu in there. So this would be one simple generic class we can create. Now why would we build such a generic class? Well, just as I said, because maybe we don't just want to store text. I might also want to store some numbers in a different data storage. So then I could create such a data storage, and setting this to number ensures that now we can only add numbers to that storage. And of course we could also set up a storage where we allow both by using a union type. So we got full flexibility there, but we give TypeScript some extra information that makes this both a flexible and still strongly typed class, just as we had it with functions. Really flexible and still perfect type support. That's the whole idea behind generic types. So here we can do that with the data storage class by storing strings or by storing numbers or whatever we want. We'll have one problem about our data storage class though. Let's say here I have my object storage. Now I can create new data storage and say in there I want to store objects, right? I want to store objects, and therefore of course we can go to object storage and add an item, let's say an object where I have name max in there. Now let's also store another object where I store manu. Then let's say we're doing some stuff in our code, and at a later point of time here I want to remove the item. I want to remove the item with name manu here. And then I want to console log object storage get items, like that. Now if we save that, we see we got an object in there that's max. So that looks good, right? Now, it's not really good. Let's say here, I want to remove max now. So now we should have manu left in the data storage. Hence, if I reload, oh well, it's still max. Now, the problem is that we're working with objects here. As you know, objects in JavaScript are reference types. Now, attached you find an additional resource which allows you to dive into reference versus primitive values. Here, I assume you know the difference because it's a core JavaScript thing, totally unrelated to TypeScript. Here, the problem is the way our class is built with this logic on how data is removed and identified. We're not really doing a good job when we work with non-primitive values. So when we work with objects or arrays. Because index auth, if we pass in an object here, will not work because technically this is a new object. It might look like this one, but it doesn't work because this technically is a brand new object in memory and has a different address. And indeed, here, JavaScript will look for the address and basically not find it. So what it then does is it removes the last element in the array here. Because this in the end returns -1, index auth returns -1 here if it doesn't find anything, which means it starts at the end of the array, that's normal JavaScript behavior, and removes the last element of the array therefore. That's why it worked for Manu, it didn't really work, it accidentally worked, but why it does not work for Max. We're always removing the last element of the array for now, since we can't identify it. Now one workaround to at least fix that is to check if we find an item. So we can check if this code here, if that is equal to -1, which means we did not find it, then we can return and make sure we don't accidentally remove the wrong item. But of course now we just fixed that bug, but we still don't have this inner state where it would work with objects. Well, the only way how it could work with objects is if we pass in the exact same object again. So here if I had my max object stored in a constant, like this, and then here I pass in max object, and I do the same here, then I'm really using the exact same object in memory, and therefore now it would work. This would be the only way to make this work. So therefore here, the better idea might be to make sure that this really only works with primitive values. So we could say that t extends string, number, maybe also booleans, and so on. So now we basically say data storage should only work with these types, and therefore objects are not allowed anymore. This might be better here because we would need a more specialized data storage, which then probably only works with objects in turn and not with primitive values, to fine-tune our retrieval logic here to maybe check for some ID in the item that should be removed. The way it works here, it really only works for primitive types, so setting such a constraint is definitely a good idea. And with that, if we save that, after commenting this out, it again works, of course. Now, needless to say, hopefully, that of course, you could have more than one generic type here as well. You're not limited to one type when you work with classes. And you can also have methods which have their own generic types inside of classes. So you could introduce new generic types in class methods if you have some generic type which only is needed in a certain method and not in the entire class. So you're really flexible there. You can use constraints everywhere. And in general, generic types are there to make your life easier and to give you that perfect combination of full flexibility. We can use any primitive value we want here, and type safety, because we know perfectly well what is stored in this data storage and what is stored in this data storage. So this combination is the awesome thing generic types give us.